Design of experiments is a systematic experimentation with a process critical factors in order to correlate these factors to process responses. In DOE with Excel we obtained a linear relationship between several factors and one response. In Response Surface DOE this was extended to nonlinear relations. In both cases we were optimizing one single response. Now we will analyze some cases where more than one response needs to be optimized. Download file multiple response.xlsm from OneDrive to your PC. We want to maximize yield and minimize cost in a process where we have identified three critical factors, which may affect both. These are the factors and levels we want to experiment. We start with a full factorial DOE with two central points, and run a simulation of the experiments in sheet yield cost simul. We then add the interaction columns, with green headers, for the analysis. We now use Excel data analysis regression to analyze yield. And the result in sheet factorial is: our square is not so good, 0.72, and all p-values are above 0.05, so this model is not acceptable. We now do the same regression analysis for cost. Our square is not good either, 0.63, and all p-values are above 0.05, so this model for cost is not acceptable either. We will now use a pivot chart to see the influence of pH on yield. The central point is not in line with the extreme values of +1 and -1, so this is an indication of curvature. The linear model is not valid. So we will do a response surface DOE for three factors. We will select the CCI design to avoid using pH values beyond the physically possible values. See Sheet RS designs. We run the experiments in the simulator yield cost simul and then add factor quadratic terms and interactions. The result of the regression analysis in Sheet RS result for yield and cost is much better. Our square values of 0.99 and 0.92. We now remove non-significant terms and repeat the analysis. See sheet reduced. These are the resulting model formulas for yield and cost. We prepare for Solver to optimize. We will ask Solver to place the pH and time values we are looking for in yellow cells T18 and T19. In T17 we put the value 1 which will multiply with intercept to leave it as it is. In T20 we put the formula to T18 times T18 to calculate pH squared. In T21 the formula equal to T19 times T19 to calculate time squared. In I22 the formula equal to sum product of I17 to I21 and T17 to T21 to calculate yield as a function of the coefficients and the values of pH and time. In O22 the formula equal to sum product of O17 to O21 and T17 to T21 to calculate cost. We will start by maximizing yield. We can maximize yield to a value of 66.9 with a cost of 63.8 with the coded values of pH equals 0.51 and time equals 0.44. We can decode these values in sheet decoding. That is, pH equals 9.55 and time equals 12.76. We can achieve a minimum cost of 40.4, at the expense of a low yield of 32.6, by using a pH coded value of 0.21, and a coded time of -0.27. We can achieve a maximum yield of 62.5, and a cost of 50, by using a pH coded value of 0.43, and a coded time of 0.17. Here we can see the maximum yield, and the minimum cost, we can obtain. Also the maximum yield with a cost below 50. We will now run 10 confirmation runs, with our estimated ideal pH and time coded values, in sheet yield cost simul. In sheet confirmation we obtain, from these results, the confidence intervals for yield and cost, corresponding to these ideal values of pH and time. Since we only have two significant factors in this case, pH and time, we can draw the response surfaces corresponding to our estimated formulas. Let us now analyze another example. We want to meet the following response specifications by adjusting the shown critical factors. So we have run response surface CCI experiments and added quadratic and interaction terms for the analysis sheet photo. These are the analysis results for the three responses, see sheet photo analysis. For each response, we only select those factors and interactions which are significant, p less than 0.05. We need Solver to calculate the values for the factors in the yellow cells, AI15, AI17. These factor values should be between +1 and -1. We specify the maximum and minimum values required in the responses. We select response edge to be maximized, as well as meet the minimum restriction of 3. Solver was able to find factor values that meet all specifications. These are some conclusions. The design of experiments could be extended to nonlinear relations between factors and responses. On some occasions, more than one response needs to be optimized. Excel data analysis regression can be used to approximate mathematical formula to each of the responses. Excel Solver is useful to optimize the process, meeting multiple factor and response restrictions. Several alternatives can be easily analyzed with Solver once the mathematical model has been validated. You can read this article in Polyhedrica blogspot.